Thanks, Katie. Um, I guess everyone can hear me at the back. I don't have, I mainly put this talk in as sort of a placeholder so that this topic gets discussed and we sort of get the views of everyone who's involved with sparse matrix development out here. But I figured I'll take the opportunity to just go through some of the basics of the sparse matrix, maybe the data structure, some of the operations, some stuff maybe that some of you haven't seen, and maybe like a little bit of a roadmap at the end, and then we can have all the various debates that we have on GitHub issues, maybe right here, about what should go in base and what should go out, and how many sparse data formats do we really need, and so on and so forth. Just a quick raise of hands. How many people out here actually have used sparse matrices or tried them out in some way or another? That's a pretty large number. Yeah, it's about 50% of the audience. That's pretty good. So the story behind some of the sparse support in Julia actually is quite interesting. I've always my research was always on sparse matrices, and I worked on these things for a long time, so I love working with sparse matrices. But I really started implementing them to actually kick the tires on the compiler. And I think Jeff might recollect we found a few early bugs, and sparse matrix performance always stresses the compiler in a variety of different ways. I guarantee you, if you write a new programming language or you put some new compiler passes, if you run sparse matrix performance tests, you're bound to find something interesting. All right. So the stuff out here has been done by a lot of people, and Andreas, Doug Bates, Tanmay back there, Simon Kornblath, Christopher. I think he just wrote an amazing interface to the MKL sparse solvers. Tony Kelman, as always, he's on top of everything, and I don't know what I've tried once in a while to squeeze in a couple of things without him seeing, but that hasn't been successful. Miles, Ian, there's tons of people who've contributed to this, either in the design or the code, and this is great, and we just need much more of this. All right. So let's get the basics out of the way. What is a sparse matrix? I mean, why should we really have sparse matrices in the first place? So just to put sort of, at least what I thought about when I first started designing this, and this kind of is nothing new with Julia, but goes back all the way to MATLAB and much before the design of sparse matrices, that you want a data structure that has a storage of, and this is the important part, max of n comma n and z. So you want this, if you have fewer non-zeros in the sparse matrix than the number of n being the columns or rows, depending on your data structure, you want to either at least store all the rows or the columns or the non-zeros, right? And whatever's the maximum. You could have data structures which is just strictly order n and z, and we are going to touch upon some of those at the end of this talk and as part of the roadmap. But this is the data structure we have right now, and it's largely motivated from the need for doing sparse linear algebra. And back in the day, it used to be the case that you had one data structure, and then you used sort of a left-looking LU maybe. So you started with compressed sparse columns or compressed sparse rows, and then you'd implement all your stuff on top of this data structure, and that one data structure had to be perfect. 20 years later now, the world is very different when these choices were made. You almost never write a sparse linear solver on your own. You call one of the dozens of packages out there. We are almost getting to a point where you wouldn't even write matrix vector multiplication on your own, because it's kind of all going the BLAS way, but unfortunately with no standard interfaces. So the question then becomes, should we continue to use these data structures or should we not? And we have continued to use the same data structure, but we do not do the linear algebra directly on these data structures. We pass them into some black box routines, and they do this amazing high performance sparse solves, and they send stuff back. Okay. But that's where the motivation for those data structures comes from. An operation on sparse matrices should take time approximately proportional to the size of the data accessed and the number of non-zero arithmetic operations on it. Now, obviously, if you're doing binary arithmetic, or if you're just doing logical, all your simple sparse matrix things, this is obvious. But what if you are doing a sparse matrix multiplication where you can't predict the structure in advance, but what you want as per this principle is that the number of floating point operations that you perform should be roughly proportional to the actual amount of arithmetic that happens on this yet undetermined data structure that will be the output. And people deal with these things in different ways, but some of these considerations are part of the underlying design. For those of you who haven't used sparse matrices, when should you use a sparse matrix? Simple answer, only when it's worthwhile. Longer answer, the data structures have considerable amounts of overhead. If you can avoid using sparse matrices, please avoid using them. Do not use these things, they are very slow. But there are tons of problems where the benefits outweigh any of the slowness, because you don't want to store the zeros, or you don't want to operate on the zeros, and that can be significant savings. But the practical answer is just try both, and whatever's faster. Like that's always a rule of thumb that works. All right, so this is the compressed sparse column data structure that we have in Julia. This is exactly the definition in Julia of the sparse matrix type. And I wish I had put a picture here, but I haven't been able to do that. So I'm just going to talk through this one. You have your number of rows and number of columns. And because it's a column data structure, what you get to store is the beginning of every column, and the beginning of the next column, and the beginning of the next column. So every column is the beginning of itself, and then sort of the index that is one before the next column starts. And all the columns are stored just one after the other. And inside each column, you have a sparse vector effectively. Like what you have is this row value, which is which row index it is, and then what's the non-zero value. The purpose for describing this data structure is so that more of you guys who haven't dabbled with this stuff can start dabbling with it and improve the performance of the sparse matrix kernels. I think I've restarted this thing many times, this notebook, so I might just as well start using Gadfly right now. All right, it couldn't have happened this fast, right? Okay, maybe the kernel was running, I don't know. All right, so this is a simple, just to look at the data structures before we move on. So I just created this artificial 4x3 sparse matrix, and I stuck in a few zeros out there, and this is what the sparse matrix looks like. Couple of interesting things that we gained from the Julia type system in our sparse matrix design, which I didn't see done nicely in systems that I have written before or used before, is easy support for different types of numeric data. At best, you get double precision, or you get complex double precision. Maybe you get single precision and complex single precision, but that's about it. In Julia, this is all just, it can be any type as long as it's the same type. This could be a string, but I'm not going to go there for this talk, or just about anything else. But the interesting thing is also that, and I don't know if people need to use this, but is that we can also use any type of integer indices in our sparse matrices. So should you really care about it, you could have a 16-bit sparse index, a 16-bit index in your values in the sparse matrices. Where it probably matters is 32-bit versus 64-bit. The default is to use 64-bit, but often people don't have sparse matrices that are in the billions, billion by billion. So you probably could save a lot of memory bandwidth by just using 32-bit integers out here. We don't do that by default. I have found the performance to be at best 20-30% faster in the best cases. But you never know, depending on what you try. All right, so this was a sparse matrix data structure, and then I created this sparse matrix A out here. I took the dense matrix A and just called sparse on it, and we got this thing right here. Right, I'm just looking inside, and I have the number of rows, the number of columns, the starts of every column. So notice that the first column here has 4 values. And so the starting point is 1, and then the next thing is starting at 5. So that's right here, but there's only 2 values out here. So 1, 5, 7, and then 9 is the end of the last column. So I have 9 elements in here. 4, 5, 6, 7, 8. Yeah, 9 minus 1. All right. And then these are the row values inside those columns. So between 1 and 5, I have column 1, and then these are the indices for those, and then these are the non-zero values. So that, in a nutshell, is so why the term compressed comes from the fact that that each column is compressed, but you don't have compression as you store the columns. So if some columns were 0, you'd still have a dense. So think of it as a dense vector of sparse vectors is how this sparse matrix is represented. And you can always ask the question, why can't I have a sparse vector of sparse vectors? Or why not just have, just to store them as an array of tuples, and you can. But each of these designs sort of brings you to a different point. You can't have one sparse data structure that is good at doing everything, and this is generally sort of, you can have a sparse data structure that can answer efficient indexing queries, but then may not be efficient for doing linear algebra. You might have sparse matrices that are good for doing, that transpose really fast, but won't be good for something else, and so on and so forth. Computer scientists also have lots of other fancy data structures with, you can imagine all kinds of quad trees and various kinds of data structures, which would be great. But in reality, what works fast is just this simple array-based storage, and that's just the world of scientific computing. Simple is best. All right. So some constructors, I think everyone's seen these. This is just your sparse identity matrix, SPI. I think we need to do something about these SPs in the names. I think they are sort of a leftover thing from the MATLAB APIs. I'm open to some ideas. I don't know what you guys would like to call these things, but I'd love to have some good ideas. All right, this is SPRAND, and this is just a sparse random matrix, a million by million, and this is the density. I like to write the density as something over the number of rows or columns, and that usually translates into the number of non-zero values per row or column. So this is giving me a sparse matrix of size million by million with, on average, one non-zero per row or column, and so that's almost what I have here. And just like the dense arrays, we print our sparse arrays nicely. We put these ... things so that, unlike in MATLAB or something, it doesn't scroll like all over the place with a million entries. All right. Now, for the purpose of this demo, I wanted to create a set of grids, because grids are just nice to work with and easy to show examples on. And I use this mesh part toolbox. Actually, I should probably find it and put it up here just because I'm using it. Oh, what happened there? This is a great toolbox. Unfortunately, the license is not great, so I won't, this code won't be useful, but this was my advisor, John Gilbert, and Shangwa Tang out here. It's a toolbox with lots of cool stuff, and I just ported over today morning some of these mesh and graph generators. Maybe I should just run one of these things. All right. So toggle header. No. Toggle toolbar. OK. So if I say grid 5 of 5, this is the 5-point grid, which means I'm going to start out with a stencil which has sort of a point up northwest, east, south. So it's a 5-point stencil basically, and this is a matrix that represents that 5-point stencil. You can kind of see that the diagonals have these values 4, and then the off diagonals have this value of -1, much like a Laplacian. And if you plot this thing, so I plotted with the SPI. This SPI command has come from Gadfly, by the way, and this is what the matrix looks like. So imagine having a regular 2D grid, and if you're on the corner, you have at most 2 neighbors. If you're on the edges, you have 3 neighbors, and if you're somewhere within the grid, you have 4 neighbors. And that's kind of what's going on here. If we zoom in, great zooming capabilities in Gadfly. So these are the diagonal values, and then if generally I'll have 4 neighbors. So I have non-zero for this guy here, this guy out here, this guy out here, and so if the diagonals are kind of square root of n bandwidth away, and depending on how you number your square, the left and the right might be sort of immediately off diagonal out here, and then the top and the bottom will be. So this is a pentadiagonal sparse matrix, pretty common, and I was able to write these constructors pretty easily actually. Let's see if I can find the code I have. So this was the code. It just constructs a bunch of block diagonals. It has this spdiags function, which I think we used to have, but we removed and called it something else, and I forgot, so I just rewrote it. And then, so pretty straightforward, right? Just with a little bit of code, you can write all these graph generators or sparse matrix generators. That's not the point. And you can get these pretty pictures. Okay, so grid 9 does the same thing, but it's 3D. So you get a 7 diagonal system. If we go in there, that's what's going on there. These are actually two things out here. All right. So that's grid 9. Okay. These are just sort of, I'm just kind of going through a very quick tour on how to create different types of sparse matrices. And this is the most common thing that you might do to create a sparse matrix, is have tuples which are row value, column value, and non-zero value, and then you create vectors of these three things, and then you just call sparse on them. So here I'm just taking random row values, random column values, and then random non-zero values, and creating a sparse matrix. The sparse method is pretty optimized, and if it finds duplicates in the same row and column position, it will sum them up or do something else if you ask it to. And that's what this random thing looks like that I just did. So you have your various sparse random matrix generators, and I did some grids, and I did the sparse identity matrix. That should be usually good enough to sort of get started, right? Okay. All the usual stuff that you'd expect works, or if it doesn't work, file an issue. All your arithmetics, if you do a plus b, a minus b, a dot star. I think broadcasting was just checked in, so that also works. Pretty much everything just works because of all the incremental work that has happened. A few performance tips to keep in mind when you work with sparse matrices. Accessing columns is always faster than accessing rows, usually. Always and usually, yeah, in the same sentence, but and there's a bug out here with IPython, which even despite my semicolon is printing stuff. But here I have a sparse matrix of a million by million. I'm summing up along the columns out here, and I'm summing up along the rows, and just you can imagine that the data structure is by columns, so just summing up something along the columns is really fast. But if you want to sum up along rows of stuff that's stored as columns, you have to do a little bit more work. I don't know if this work justifies it to be this much slower, but I think this is not completely unreasonable either. So another one. All right.
Because of the comment. If you take the comment out.
Sorry, is the comment that's getting me? Okay. Yeah, I think I added the column the comments later, so that's. Just the last one. I see. Okay. But I kind of like it not being asymmetric. All right. So here's a random permutation of of a vector going from 1 to a million, and I'm just doing, in this one I'm permuting the rows, and in this one I'm permuting the columns. And the one where I permute the rows is significantly faster than permuting, oh sorry, it's the other way. This is seconds, yeah, that's what I would have expected. So the one where you're permuting all the rows within a column, that's a lot of work compared to columns where you just kind of, copying bunch of stuff all over the place. So a huge difference, right? And so just keeping this in mind, that there can be a huge asymmetry between how you access rows or columns when you operate on sparse matrices. Just keeping this one point in mind can greatly help you write high performance sparse matrix code. The other bad thing that I see people do, and I'm pretty sure most of the people in this room know that they shouldn't do this, but for those of you, who are going to try this out at home, this is the bad way of constructing sparse matrices, and this is a good way. And basically do not assign into a sparse matrix. That's the lesson. and as long as you do that, things will be good. So here I'm constructing the same thing. I'm just picking up, random values, random indices, but instead of storing them in the sparse matrix, I'm pushing them into these vectors, and then I'm constructing with sparse. And this starts begging a lot of questions, right? Like with all the advanced data structures and all the capabilities that we have in Julia, like can this not be automated, right? Like can we just not have a data structure where we do this, we accumulate these updates lazily and then maybe call sparse automatically? And this has come up and everyone has thought about it, but again, if you start doing that, then everything else has to test for these updates to be applied lazily, and every single operation, and then that puts burden on someone else somewhere else, and costs performance elsewhere. But so this is the bad and the good. So the bad was I had to find a problem size that would actually run while I was doing this demo. So I just went with 300 by 300, and this is already, you can see, orders of magnitude slower. All right, so that said, I'm going to jump a little bit into sparse matrix factorizations, and a lot of this work has been done sort of steadily for a while, and I think Andreas is leading the torch with this one, carrying the torch on this one. Just so that I can make nice pictures, I'm going to just work with very small grid sizes. So this is a 5-point grid again, like I started with. This is a convenience function that we wrote today morning, but I think this is going to go away, right? Like, all right. Let me actually show what's going on first. Okay, so I have this grid here, and this is what's happening. So I just have this matrix with the 4s and -1s like we saw before, and then I'm just doing a Chol fact of this, which looks like this. So I got something with these many non-zeros, and then if I say get CSC of Chol fact of G, which is just this helper function, but that shouldn't be required anymore once things are patched up. So this is basically extracting the Cholesky factor from the sparse factorization. All right, and now all I'm doing is a SPI plot of this. So SPI plot is basically just a sparsity pattern plot. Wherever you have zeros in the matrix, you get nothing. Wherever you have something in the matrix, you get a color. And all the magic of Gadfly and color maps is happening here. So you can kind of also see the density of these plots. So if you guys remember the matrix, it was a pentadiagonal system. There were 5 diagonals. Now I did nothing. I just did a Cholesky factorization of this matrix, and this is what I get. So I get the lower triangular factor by default, and this is what the fill looks like. So if let's look at how many non-zero values there were, just to get a sense of these things. There were 460 values originally, and now after the factorization, it's filled in. Where is this thing gone? Okay, I need to do it here maybe. Okay, that will show me what it's got. So 440 and 648, right? So that's this starts growing pretty rapidly and pretty fast. So if I do larger ones, I think I should try a few of these larger ones. Let's just get there. Okay. Yeah, we'll just stay with Cholesky for a little bit longer. So let's get. Am I not gonna like if I do this? We'll try this. Okay, let's just do a Chol fact of. So this is, when I say grid phi of 1000, actually it's a grid of 1000 by 1000, which means the sparse matrix that represents it is 1,000,000 by 1,000,000. And so I got these many non-zeros out here. And then if I just did the NNZs of this thing, I got, oops, I shouldn't have done that. Okay. Right, let's just do one more of these. I think it happened pretty fast, so we can do it again. So if you look at the history behind some of this stuff, it's really quite fascinating because Intel has given us all these amazing Moore's law increases in solver performance, in chip performance. But if you plot the improvements in sparse solver performance or even dense solver performance, it actually outpaces the improvements in chip performance, in hardware performance, and that's just because of all the amazing work people have done with sparse solvers over the last 2 or 3 decades, and all of that is right here within in Julia in a few keystrokes. All right. So this thing blew up quite a bit, and so this was what we started with. Right. So if you didn't ask Julia to do anything, I mean, if you didn't know anything about sparse matrix factorizations, and you just did it the first time, you'd probably be surprised to find out that you run out of memory if you had a large enough matrix. And in this particular case, for a million by million, without sort of knowing any of this stuff, you asked Julia to do something which probably asked some black box sparse matrix library to do something, and it did as good as it could, and it came up with fill that was about 11 times more than what the matrix started with. All right, so that's just good to know. And I'll come back to this point in a little bit, but in the meanwhile, the same thing with LU factorizations. So the same API as dense LU factorization. Oh, I shouldn't have done that. I was hoping to have a smaller one. Okay, let's just do this. Oh well. But let's keep it small, otherwise Gadfly is not going to be able to plot it. Gadfly brings everything back to the front end, so I think you don't want to plot something with millions of non-zeros in it. But Andreas gave me a cool routine that lets me do that as well, so we'll look at that as well in a little bit. But okay, so this is the lower factor, and then this is the upper factor. It kind of looks like it starts out sparse, and somehow some magic has been done because things look sparse when they start out up there, and then as you kind of go down, something changes, and things become denser, and that's just how all these sparse factorizations work. In 0.4, we also have QR factorization, and so you can solve least square systems. Simple example. I don't think I need to run through this. This is the least square solution for that system that was 1000 by 500 sparse system. Okay. So bottom line, a lot of the basic sparse direct solvers that are needed for doing sparse linear algebra and for various other applied domains that use sparse matrices, a lot of that infrastructure is actually built into Julia. It's reasonably fast. It picks reasonably good defaults, and keep writing to us if you find it doing stuff that you don't expect. Okay, but now back to this point about the filling of the Cholesky factorization. I'm just talking about these things because I think they're kind of newer, and maybe people know about this, but we haven't stretched Julia to some of these things, and I just thought it was fun as I was playing with it. So we got, I need a smaller G out here to start with, so I'm going to say, just to be sure, that. And a new command line argument was introduced. So while doing a Cholesky factorization, you can tell Julia, do not do the default fill reducing permutation that you would use. So the way sparse factorizations work is that you have fill reducing permutations. The system actually computes one and then permutes the matrix. May not explicitly permute it, but there's a fill reducing permutation applied, and when you do that, you get much lesser space used. But you can turn that off by just telling it don't do anything, just go in the order I gave it to you. And this is what happens when you do that. Right? So I just said the permutation is one, there's no permutation essentially, right, for this matrix of size 100 by 100. And now I plotted the Cholesky factor, and you see it just started filling up all the way, and now this is completely dense. As you can imagine, if you had a much larger matrix, this would completely blow the memory and not solve at all. All right, but if we now, let's just try a random permutation, right? and see what happens. So on this particular case, I tried a random permutation and I got 1200 non-zeros. I think I should print what happened here as well. So let's just look at Chol fact of G. Right. So the default thing gave us 648 non-zeros, and you know, if you just apply some random permutation, you would get 1200 non-zeros. And that's what it would look like. It's as you can kind of see, this already looks much denser than the pictures I showed you before. Yeah, and this is what it looks like if I don't give it any permutation. So you're already kind of seeing the, you know, the effects of all these combinatorial techniques, that if I don't do anything, then I get something that's really bad. If I do something random, it's still quite bad. And then you can do things that are significantly better. Now, you know, one of the key things that we've always stressed upon with Julia is composability, right? Composability of the APIs, composability of the data structures, and just with various packages and so on and so forth. And here's a package that Doug had written a while back, Doug Bates, the Metis package, and then graphs, I think was Dahua, is that right? Dahua and John and a bunch of other people. What if I can represent this sparse matrix as a graph and then use the Metis package to find, you know, do a nested dissection, get a permutation, feed it back into my sparse Cholesky solver, and see what happens, right? So these are three packages that were three set of things that were probably never envisioned to work directly with each other, but are natural that their APIs should compose. And we have a long way to go there, but the cool thing I think is that we just got this to work at the very least. All right, so first we'll do the simple case. So let's get, I'm just gonna pick the same grid but 2500 by 2500. Convert this to an adjacency list, and node ND is the nested dissection. So the nested dissection is basically doing graph partitioning and then recursively doing it until it finds an ordering that works well, and that's what happens there. So I just got this thing out here. This is the default Cholesky factorization in Julia, and this is the one with the permutation. So you can see this didn't do quite as well, even though I computed a fill reducing permutation outside using a graph partitioning software. So Metis is, by the way, a project it's from the University of Minnesota, and George Karipis and Vipin Kumar. It's a C library. It was easily wrapped in Julia, just like many C libraries often are. And I got that node ND thing from there that Doug had written, and I fed it back into Cholfact, which was just updated a few days ago. All right. And that's what happens. So it took about the same amount of time to solve, but the number of non-zeros were larger. Now I'm going to try it on a larger problem and see if it's any better. And anecdotally, nested dissection is supposed to work sort of much better as you go to larger matrix sizes, and we are going to test this out without knowing any theory about this stuff. We are just going to try it out, like right now. All right. So here is, all right. I would just believe that this permutation is of the right size because I just computed it. And this is the regular Cholesky factorization on the large matrix. And then this is the new one with the permutation that I just computed. Okay, so yeah, there we go. So by doing this additional amount of work, this was actually this actually resulted in a meaningful amount of savings. And this is what we got, right? So it's 45 million non-zeros in the filled up Cholesky factor as compared to the default that is built into Julia, which was 58 million non-zeros. Pretty cool. I think this is, you know, so the point again here was to show the composability of all these various things, and the kinds of things you can do with Julia that are usually not otherwise exposed in many other systems. And I'm just going to show what this thing looks like as the last thing on. I'm guessing this is too much about Cholesky factorization than most of you guys probably care to hear about. But I figured you guys have already seen and used much of the sparse matrix stuff, so I wanted to do something that was a little interesting. All right, so this is what the default thing looks like. So by the way, this is the my spy that I got from Andreas today morning. It just kind of tries to trick Gadfly into doing something smaller. And this is what this looks like. And I'm going to show you what's different, even though it might just kind of look obvious. But just stare at this picture. Do you observe any recursive structure in it? Maybe a little bit, but maybe not. I don't know. It's not pretty obvious to me, but here you can very clearly see a recursive structure, right? So this is the first separator that was computed. So imagine you had the big 2D grid, and imagine the separator would probably have been something down the middle, and it split the matrix, split the grid into two parts. So you got this, and then you got the next separator, and then the next separator recursively in each of these grids, and so that's nested dissection at work. And you can just kind of eyeball this and see it in Julia, and this is supposed to be provably better asymptotically, and that's exactly what we just saw. So this kind of stuff is really the goal of what we want to do with a lot of our sparse matrix work in Julia. We want it to be composable. We want it to have good APIs. We want it to be really high performance. We want it to be multi-threaded. We want to use all the crazy stuff that that Intel's going to put in with all the SIMD stuff. I don't know how that's going to happen with all these irregular data structures, but with Arch in the audience, I feel like it'll somehow magically happen. All right, so this is the state of affairs as they stand currently. Where do we need to go from here? So one obvious thing that has come up a number of times is we want more different sparse representations. Obviously, the CSC is just one of them, and the next obvious one that people have asked for is CSR, compressed sparse rows. And I think people who work a lot on iterative methods, are there people in the audience doing a lot of iterative methods? Maybe I know you are for sure. Yeah. So these guys usually prefer row-based storage for good reasons. And I think we had Tanmay, we had a pull request, but which never got merged because all the code was effectively getting written twice. That's not a good sign. That means you have bad abstractions, right? If you're writing the same code twice. Julia is about writing the code only once, as we all know, and not writing it twice, or like Shashi, you talked about four languages. The 4-language problem, no, right? Yeah, so just once. So, and this is something that I don't have a good answer to. Like, how do you express all these irregular sparse operations using an abstract API, such that can we have some magical iterators that are really high performance and allow us to express all the sparse matrix infrastructure just once and get it to work at least in 2 cases, rows and columns. By the way, this has been achieved with the dense stuff thanks to Matt's work. So just if abstractor is with abstractor is just having get index, scalar get index, you can pretty much just get all the array functionality, right? Okay, thank you. I'm almost done anyways, yeah. So we need higher performance sparse matwek, and we need to go beyond 2D, and that's basically what needs to happen. So thank you.